this second session of the European Non-Associative Day online. I hope you're all suitably refreshed and looking forward to the next set of talks. And the first talk in this session is to be given by Pavel Kolesnikov from the Sobolev Institute of Mathematics in Russia. And the title of the talk is Derived Non-Associative Algebras, Identities and Embedding Problem. So, Professor Kolesnikov.
Thank you very much. I'm very grateful to the organizers for inviting me to submit a talk here at this seminar. But in order to start, I need rights to make screen sharing. I think our administrators should do something so that I can share my screen. Oh, good. Thank you. Now, can you see my screen?
Yes.
Oh, thanks so much. What I'm going to speak about today is mainly based on joint work with Borzhan Sartayev and Farukh Mashurov from Kazakhstan. And the main object I'm going to speak about is a very simple one: algebras with derivations. Well, something strange seems here. Now it's better, I think. Suppose we have a binary algebra that is a linear space equipped with one or more binary operations. No associativity or commutativity is assumed. And suppose D is a derivation of this algebra that is a linear map which satisfies the Leibniz rule. If we apply the operator to the product, then we have to apply it first to one argument and then to the second argument, as in the beginning of calculus. The notion of a derivation is very well known. In order to be a derivation of an algebra with multiple operations, D has to satisfy such a rule, the Leibniz rule, for each multiplication operation. Then let us introduce two new operations. For each multiplication mu in the initial algebra, let us consider two operations, left one and right one. Why I call this stuff left one? Because we have to apply derivation D to the left argument, to A, and then multiply dA and B. And similarly, to define the right operation, let us apply the derivation to the second argument. What we obtain is the same linear space equipped with a double number of operations. If there was only one multiplication, then we obtain two operations here. If there were more than one operations, then here we have just duplicated number of operations. Let us call this system derived algebra. It is related with the initial one. The initial one, say A, mu, and maybe more operations, and D from derivation space. So we derive this new system. And as usual, the first problem which naturally appears is to describe what are the identities that hold on derived algebras if the initial algebra satisfies some family of identities. For example, if we start with associative algebra, what are the identities that always hold for derived algebra. In terms of varieties, we can state the same problem as follows. Suppose we have a variety of algebras, say variety var, a class of all algebras satisfying some given family of identities. Then we may consider all derived algebras constructed on algebras from the initial variety var and all possible derivations. And then consider all those identities that hold on all such derived algebras. What we obtain, let us call derived variety and denote it, for simplicity, d var. So derived variety of var. In other terms, we may consider the class of all derived algebras and generate the variety in the ordinary sense. Consider Cartesian products, then subalgebras, then homomorphic images, as it is usual in universal algebra. This construction, the construction of a derived variety, is actually motivated by the following well-known and maybe even classical example. Suppose we start with algebra with one associative and commutative operation mu. So the variety var is the variety of both associative and commutative algebras. Then the left operation, mu left, is equal to dA of b, which is obviously the same as b times dA, which is right operation applied to b and a. So the algebraic structure on a derived algebra can be completely described by single operation, say this one. And it is easy to check that this new operation satisfies two identities. I have chosen the left one. So what I obtain is left commutativity and right symmetry. These identities are very close to those identities Oskar Jumadildaev mentioned in the beginning of our seminar. These are the identities of Novikov algebras. But if you choose the circle operation to be the right one, then the resulting identities would be right commutativity and left symmetry, just symmetric ones. The class of Novikov algebras actually emerged in 1979 in a paper by Gelfand and Dorfman related with formal Hamiltonian calculus. And then it also appeared in a paper by Balinsky and Novikov related with Hamiltonian formalism for partial differential equations. And there was a nice story about structure theory of Novikov algebras, but what is essential for us today is the result by Jumadildaev and Le Fall of 2002. They actually proved that the derived variety for commutative algebras coincides with the variety of Novikov algebras. That is, these identities are easy to check for such an operation on a commutative algebra. But why these two identities exhaust all independent identities satisfied for such an operation? This is exactly the result by Jumadildaev and Le Fall. They proved that the free Novikov algebra can be embedded into free commutative algebra with a derivation. So if we speak about identities, then identities are actually relations on the free algebra. So if the free algebra embeds into differential algebra, then there are no other identities that hold for this circle operation. Well, but what about an arbitrary Novikov algebra? If the free Novikov algebra can be embedded into differential commutative, then why an arbitrary one can also be embedded? The positive answer was found by Bokut, Chen, and Junk in 2017. They proved that, in fact, they used characteristic 0. Oops, sorry. They proved it in characteristic 0, but the methods actually work in arbitrary characteristic and even over a commutative ring. So every Novikov algebra can be actually embedded into an appropriate commutative algebra with an appropriate derivation. So we may generalize, try to generalize this statement in the form of the following problem. Suppose we are given a variety of algebras, and suppose we can derive what are the identities defining the derived variety. Suppose we know what is d var. Then, is that true that every algebra from the derived variety can be embedded into an appropriate algebra from var with a derivation? Before I state more or less general theorems, let us look at examples. We have already discussed what happens in COM. Commutative algebras, they provide us Novikov algebras. But what happens if we choose Lie algebras, for example? Then, of course, because Lie algebras are skew commutative, we can express everything in terms of only one operation, say this one, DAB. It is enough to get only left one or only right one. It has been known in folklore that there are no identities that hold for such an operation for all Lie algebras and for all derivations. So this new operation does not satisfy any identities. But what for embedding problem for this one? It can be solved positively. So in fact, every magnetic algebra can be embedded into an appropriate Lie algebra with a derivation. This is actually an easy exercise on Grobner-Kirchhoff basis theory for Lie algebras. And it was shown as a remark in my paper with Baurjon Sartaev and Aybola Razgaliev. So for Lie algebras, the derived varieties coincides with the variety of all non-associative algebras with one operation, and the embedding problem solves positively. Other natural varieties, for example, associative algebras. For associative algebras, we have to consider two operations because we have no symmetry for multiplication. Two operations, left and right ones. They are related by two identities that were found by Ladey in 2010. These identities are stated here. They are also easy to check. It's easy to check that these identities actually hold on every associative algebra with a derivation, if we consider these two operations. But why these identities exhaust all independent identities that hold for such operations on all associative algebras with all possible derivations? It follows from a positive solution of the embedding problem, which was recently published by Bourgeon, Sartayev, and me. The methods of proving a positive solution of the embedding problem are somehow similar to those applied for Novikov algebras, but we also found an independent way how to prove that embedding problem is positive by means of rewriting system, Grobner-Kirchhoff basis, and all that stuff. The main results I would like to speak today are the following 3 points. First, I'm going to describe how can we find all defining identities of the derived variety if we know the identities, defining identities for the initial variety var. This computation works well if we deal with quadratic varieties. So quadratic means defined by identities of degree 3, like those associative, Poisson, Lie algebras, they are all quadratic. Also, we can state a sufficient condition for a variety var, sufficient condition for var, to be sure that the embedding problem solves positively for all algebras from the derived variety. So we describe the properties of var so that every algebra from the var embeds into an appropriate var algebra with derivation. This is just a sufficient condition. A sufficient condition, it is not necessary. For example, the variety of Jordan algebras, it is not quadratic, however, but Jordan algebras do not satisfy this sufficient condition. However, embedding problem solves positively for Jordan algebras. And finally, I will show an example of a variety for which the embedding problem has negative solution. So this sufficient condition is not satisfied for this particular variety. And also, it is necessary to show, of course, that there exist algebras in the derived variety which cannot be embedded into any var algebra with a derivation. But first, before we go to these results, let us discuss what is known not for derivation, but for integration operators. The formalization of integration is known as Rota-Baxter operators. Oskar Jumadildaev discussed Rota-Baxter operators in the beginning of our seminars. Let me briefly recall the definition of a Rota-Baxter operator of weight 0. Again, for binary algebra, a Rota-Baxter operator is a linear map which satisfies the following identity. This identity actually represents integration by parts in some sense. Oskar Jumadildaev also showed that integration operators, they provide essential examples of Rota-Baxter operators. I will speak only about weight 0 operators. And in a very similar way, we may construct left and right derived operations like that. Just instead of a derivation, let us apply a Rota-Baxter operator. These operations are also very well known because the analog of a derived algebra, in this case, it turns out to be what is known as dendriform type algebra. Such algebras were studied by Ladey, in particular, in his paper of 2001. He has a systematic study of dendriform algebras and all those similar algebras. But since that, let me state just a final answer. If we start from a variety var, then the derived algebras obtained from all algebras from var with respect to these operators, they generate the variety which is usually denoted pre-var. It is known as dendriform splitting of the variety var. I'm using the terminology by Bellier, Gue, and me of 2013. They described the procedure how to write the identities of pre-var. Of course, let us deal with multilinear identities only. This is not a restriction in characteristic 0, but to be precise, let us speak about multilinear identities. If we have some family of multilinear identities defining the variety var, then we may simply rewrite them to get the identities defining the splitting variety pre-var. The examples of such a splitting are the following. For example, associative algebras. If we apply dendriform splitting to associative algebras, then what we obtain is exactly what was called by Ladey dendriform algebras. But I have already used dendriform as a generic title for all this theory. So dendriform algebras are pre-associative algebras exactly. Lie algebras provide very interesting example because pre-Lie algebras emerged in 60s. They were introduced independently by Winberg, Kashul, and Gerstenhaber in various problems related with geometry and homological algebra. Pre-Lie algebras, they also defined by only one operation, because Lie algebras have symmetric multiplications, two-symmetric multiplication. Only one operation is enough to choose. If we choose right operation, then what we obtain would be left symmetric algebras. Left operation provides us right symmetric algebras. They both known as pre-Lie algebras. This is why I'm using the same pre-associative and so-called pre-var algebras for all these theories. And the third one, the third example, if we apply dendriform splitting to commutative algebras, associative and commutative algebras, then again we need only one operation, because commutative operation is Q-symmetric, just symmetric. And the associativity identity turns into this strange-looking identity, which is known as the defining identity of symbol algebras. Oskar Jumadildaev has already told about symbol algebras in his talk today. So symbol algebras, they are pre-commutative algebras, dendriform splitting of commutative algebras. And what about the embedding problem? So as for identities, everything is more or less clear in this integral integral settings. But what about embedding? The embedding problem solves positively for all multilinear varieties. For every algebra from dendriform splitting variety pre-var, there exists an appropriate algebra from the initial variety var with a Rota-Baxter operator, such that this pre-var algebra embeds injectively into A, so that the operations are given by the splitting rule, by this one. So for integration setting, embedding problem solves positively. Identity problem can be solved by routine procedure of dendriform splitting. So let us return to derivations. The natural method to deal with multilinear varieties of algebras is to switch to the corresponding operads. The notion of an operad is usually attributed to May, who introduced it in 1970 and a little bit later. But actually, Vyacheslav Artamonov introduced the very same notion under the name of a clone of algebras a little bit earlier. What is an operad? In a few words, an operad, it is a category with a single object, but at the same moment, this is a kind of an algebra. It is somehow similar to how we may consider a monoid. A monoid is an algebraic system with one operation, right? On the other hand, monoid is a category with a single object. So operad is the very same as monoid, but morphisms or in this category may have multiple arguments. So operad is a monoid with multiple arguments for morphisms in some sense. Formally speaking, an operad is a family of linear spaces indexed by natural numbers. Each of them, I'm speaking about symmetric operads, so-called symmetric operads. Each of them is a symmetric module. The symmetric group acts linearly on this space. And this family of linear spaces is equipped with composition rule. Composition rule is a family of linear maps like that, which can be thought of as a superposition or a substitution. Just suppose each ON consists of multilinear transformations of a linear space. Then, given a transformation with n arguments, you may substitute transformations with other number of arguments, so that the result, the composition, would be a multilinear map with this number of arguments. So, in order to understand what is an operad, just remember about composition of multilinear maps. In order to formalize this notion, one has to add axioms. Actually, there are 3 axioms, including associativity of composition. There should exist an identity element, which is identity with respect to composition. And one has to claim equivariance of the composition relative to the action of symmetric group. Roughly speaking, if you permute arguments here, symmetric group action acts like permutation of arguments on multilinear maps. If you permute arguments here and also here, that would be a certain permutation of arguments from here. That's all about equivariance. These axioms are very natural. So, For every variety of algebras, we may construct an operad. The corresponding operad is constructed in the following way. Consider the free algebra in this variety in countable number of variables, and then choose all those elements that are multilinear of degree n, depending on the variables x1, xn. That will be exactly the space On for an operad corresponding to a variety var. Symmetric group Sn acts on On as a permutation of variables. And composition. Composition is a substitution with renumeration. For example, if you consider something like x1, x2, and consider composition with x2, x1, and x1, just substitute this one for the first one to get x2, x1, and then the remaining should be numbered as x3, and so on. This is a very natural object, actually an operad related with a given variety. If algebras in the variety var were binary algebras, then the corresponding operad is generated as an operad relative to composition and symmetric group action by the space of binary operations. So these x1, x2, along with x2, x1, they generate all possible expressions here. And conversely, given an operad, suppose it is a binary operad, so it is generated by its second component, we may construct a variety. Variety would be the class of all morphisms from this operad, morphisms of operads. What is a morphism of operads is very natural. Family of linear maps preserving symmetric action and composition and identity as well. Morphisms from the operad or two vector spaces. Each vector space with multilinear operations is also an operad. So every morphism, to define a morphism, is just to define operations O2. But binary operations on a vector space are exactly those mu. So given an operad, a binary operad, gives us a class of binary algebras, and the identities defining this class as a variety, they correspond exactly to the relations, defining relations of the binary operad O. So we say operad is quadratic if the identities are of degree 3, that is relations, they are of degree 2. Because these relations, they are relations for operations. And there is a famous paper by Ginsburg and Kapranov, where they, in particular, introduced what I can call an arithmetics of operads. In the paper, we deal with binary and quadratic operads. But those structures I'm going to use, they can be applied not necessarily to quadratic, but for arbitrary binary operads. One of such operations is so-called Adamar product. Adamar product is nothing but tensor product of operads. In order to construct this space, just consider linear tensor product of the corresponding linear spaces. symmetric group acts in a component-wise way. Composition is also defined in the component-wise way. But this operand, Hadamard product, is actually very large. Even if even if O and P, even if they were quadratic, if they were binary, even if they were binary, the resulting operand may not be binary. This is why we can define what is called Manin-White product of operands. Just consider sub-operand in the Hadamard product generated by binary operations. This operand is definitely binary because by definition it is generated by binary operations. So Manin-White product is a sub-operand, but not necessarily coincides with Hadamard product. Let me mention also that Ginzburg and Kapranov also introduced so-called Manin-Black product and Kazhul dual operand. But I will not need this construction in my talk. The first result I would like to speak about is the description of derived variety. Suppose var is a multilinear variety of binary algebras, then the operand governing the derived variety is exactly the Manin-White product of the operand governing the initial variety var and the operand of Novikov algebras. So in order to get the identities defining the derived variety, we have to compute the Manin-White product of these two operands. Let me briefly compare this result to integration settings, what we have for integration operators or Rota-Baxter operators. It was proved almost simultaneously by Billier, Gu, and me, and Kubarev and myself, that the operand governing the dendriform splitting for a multilinear but quadratic variety is actually defined by Manin-Black product of the initial operand and the operand governing pre-Lie algebras, those Winberg, Kazhul, Gerstenhaber algebras. In the case when the initial variety was quadratic, Novikov variety is also quadratic, of course. It is defined by identities of degree 3. Then calculating the Manin-White product is, well, not simple, but a routine linear algebra problem. One of the possible ways is to find an intersection of two subspaces in high-dimensional linear space. So we may try to apply this procedure, Manin-White product, to the variety of Zimbil algebras. By the way, I mentioned Kazhul dual operands. So the well-known variety of Leibniz algebras, non-skew commutative Lie algebras, if we apply Kazhul duality to the operand governing Leibniz algebras, then what we obtain is exactly the Zimbil algebras. So Zimbil is just Leibniz read backward, Leibniz, Zimbil. Let me recall that Zimbil algebras are defined by an identity like that. as I said, this is a routine problem, how to find the identities of derived variety. This multiplication in a simple algebra has no symmetry. It is not non-commutative, non-skew commutative. So in order to describe the derived variety, we need two operations, left and right ones. And there are four identities. It turns out there are four identities defining the derived variety. These identities, these four identities, are stated here. But let me also make the following observation. Simple algebras are pre-commutative algebras. Derived commutative algebras are Novikov algebras. In this particular case, we can apply dendriform splitting to Novikov algebras. Dendriform splitting is also an easy procedure. It doesn't require any linear algebra, it's just rewriting something in some sense. We may apply dendriform splitting to Novikov algebras to get the identities that define pre-Novikov algebras. It turns out that derived simple algebras and dendriform Novikov algebras, these two classes actually coincide. This is a problem I do not know the answer. If for every variety var, these two operations, getting derived algebras and getting dendriform splitting, do they commute? I don't think this is the case, but still I don't have any counterexample. But for commutative algebras, these two operations actually commute. It can be found by straightforward computation. Now let us turn to embedding problem for derived variety. The sufficient condition for embedding problem to be solved positively is the following. Suppose the man-in-white product coincides with the Adamar product. In general, let me recall, this is a sub-operand. If they coincide, then every algebra from the derived variety can be embedded into an appropriate algebra from var with a derivation. So this equation, let me select it here. This equation is a sufficient condition for positive solution of the embedding problem. Let us consider some examples when this condition holds. For commutative algebras, it holds because commutative algebras, the operand of commutative algebras acts as an identity with respect to both Adamar product and man-in-white product. So for commutative algebras, apparently, embedding problem is positive. For associative Poisson or Lie algebras, also we have a positive answer. This operand actually coincides with Adamar product. But for Jordan algebras, this equation doesn't hold. However, the embedding problem can be solved positively. It is also an easy exercise on Grobner-Chershov basis theory just for associative algebras with a derivation. So this sufficient condition I mentioned in the theorem here, it is not necessary, definitely. But it turns out that for simple algebras, those pre-commutative algebras, this condition also doesn't satisfy, and also For the variety of Zimbil algebras, we have negative solution to the embedding problem. It was quite unexpected because usually all those general properties that hold for ordinary algebras, they also hold for pre-algebras. So like pre-Lie algebra can be embedded into pre-associative algebra and all that stuff. But it turns out that for Novikov algebras, we have a negative answer. Pre-Novikov algebra cannot be embedded into a pre-commutative algebra with a derivation. So what can we state? The embedding for what we have for ordinary algebras, this embedding doesn't hold for pre-algebras. It is not in, this property is not inherited in the dendriform world. Now, here I have a couple of minutes, I think. I have stated a brief idea of the proof, how to construct such an example of a Zimbil algebras. Let us consider free Zimbil algebra with a formal derivation. It can be considered as a free Zimbil algebra in infinitely many variables, and a derivation, suppose the derivation acts like that. What we obtain is a free Zimbil differential algebras. Now introduce two operations, those left and right ones, and then consider the sub-algebra in the derived algebra generated by initial variables A and B, generated with respect to these two operations. What we obtain would be a free derived Zimbil algebra, because we have no other identities apart from those that come from the free algebra. And then choose an ideal in this algebra generated by the square of B, which is equal to BB prime. And then it is more or less straightforward to show that the following element, which actually belongs to V because it can be expressed in this form, but it also belongs to the ideal generated in Z, in the Zimbil algebra, not derived, but initial Zimbil algebra, but it doesn't depend to the ideal I, which was generated in V. So the idea is very similar to what was done for constructing an exceptional Jordan algebra, which is a homomorphic image of a special Jordan algebra. The idea is apparently the same. So thank you for your attention. I'm actually finished.
Thank you. Are there any questions or comments? I think there's one on the chat.
Yes. Any easy example when Adamar and Manin products are the same? I've also already mentioned. Let me return to my slide. The simplest one is to get one of them commutative. This is the simplest one, because for if var is commutative, then actually O com times any operand is just the same as P, and this is the same as O com Adamar P. The operand of commutative algebras acts as an identity, but also associative Poisson and Lie algebras with Novikov algebras, they also have equality. As far as I remember, I'm not so sure. I have already checked alternative. For alternative algebras, we also have an equality. But for single algebras, for example, no. So.
Okay, are there any further questions or comments? Okay, so can we thank Professor Kolesnikov for his very interesting talk? Okay, so the next talk will start in about 10 minutes time on the hour, 12 o'clock GMT. So there'll be a break of about 10 minutes now.